Alright, let's get started. Welcome to 3030, and today we are going to discuss lecture 17. So this is about the static random access memory, SRAM. We have talked about the memory technologies in the previous lecture, where we have an overview of the memory hierarchy, and you have seen that for different levels in the memory hierarchy, we will use different memory technology for that. And then for the cache, we are going to use this SRAM technology. And today we are going to discuss the SRAM technologies in more details. So this is a reference chapter of the textbook. And this is the guest lecture video from Professor Asif Khan. So let's first look at the SRAM cache evolution from a historical perspective. So here in the 1985, this is a typical computer system with a memory hierarchy. Here we only have one level of cache. And also this level 1 cache is off-chip. Off-chip means it has a separate chip than the processor, where in the processor you will have your multipliers, adders, ALU units, and so on for the logic control and computation. But the computation needs to fetch the data from the cache. But at that time, the cache is another separate chip. And this is in 1985, and clock frequency is only like 16 megahertz. And later, the trend is that to have more levels of the cache. For example, here in 1989, we have two-level cache, and the first level cache is merged into the processor's chip. But still, the level 2 cache is off-chip. So in this case, then clock frequency is 25 megahertz, and the L1 cache becomes 8 kilobytes. This one. And then in 1999, all the caches are on chip, and at that time, typically we have two-level cache, L1 and L2, and the clock frequency increased to 1 gigahertz, and then the level 1 cache 32 kilobytes, level 2 cache 256 kilobytes. And recently, this is the typical three-level cache architecture in the modern processors. And in this example, the clock frequency is 2.5 gigahertz, and level 1 is 256 kilobytes, level 2 is 1 megabyte, level 3 is 8 megabytes. So this is the typical specs of a processor today. And if you look at your, for example, your computer processor spec, maybe it's an Intel i5 or Intel i7. If you go to that model number of the Intel's processor, actually it will list the specs for the cache size for each level, and you can see what kind of capacity you have there. So this is a general trend, and today we typically have this kind of three-level cache in the processor. As you can see here, we have the increasing capacity from L1 to L2, from L2 to L3. So this is consistent with what we discussed in the previous lecture about the trade-off between the capacity and the speed or the access latency. So for the L1 cache, it's small, but it's fast. For L3, it's large, but it's slow. So this is a trade-off we have. And before we talk about the SRAM, we first need to understand what is RAM. Okay, RAM is for random access memory. And random access memory means that when you access the data, which means either you read the data or write the data from the memory array, you spend almost the same time irrespective of the physical location of the data. So that means you can independently read the data or write the data from the memory array. No matter where the data is, you almost spend the same time to read the data or write the data. So you don't need to worry about the location of the data. So each data here is independent with each other. So I see there's one question from the chat. So the question was, by large, you mean in terms of density? You are talking about the previous slide. When I talk about the large, I'm talking about the capacity. Yeah. The capacity of the level 3 cache is large. Yeah, the level 3 cache capacity is large. In other words, density is low. Density actually is 1 over the area. So then, capacity is 1 over density, actually. Oh, sorry, I make it a mistake. So yes, they're proportional. So the capacity here is large, and also it has higher density. It's 1 over area, that's correct. And area for the L3 cache is each cell is smaller, so the density actually is higher, and the capacity is also larger. That's correct. So let's go back to here for the random access memory, and each bit is independent. You can read or write independent with each other. And here we have the general organization of the memory array, and we have discussed that in the previous lecture. We have this horizontal line, and we call it row, or we call it word line, or in short, we call it WL. And also we have the vertical line, and this is like a column, and then this is bit line, and sometimes we call it BL. So at the intersection between the word line and bit line, we will have the memory cell to store the data. And for the SRAM case, we have the SRAM cell. For the DRAM case, we have the DRAM cell. And also we have those peripheral circuits to do the decoding. And we talked about that in the previous lecture. So you need to have the column row address as input, and then you need to decode that. If you have 10 bits, then you would have 2 to the power 10 word lines or rows. So similarly for the column side. So this is a generic for the memory array. We always have this 2-dimensional array with many rows and many columns. So this is random access. That means no matter which location the data is in the array, you spend almost the same time to read or write independently. In contrast, some of other data storage, such as the hard drive, or you may have this CD or DVD, or even older magnetic tapes, the time required to read or write the data varies significantly depending on their physical locations in the recording medium. So for example, for the hard drive, you need to spin or rotate the drive, right? And then your head of the reader need to mechanically stick the track and then go to the location, depending on the distance between your header of the read and the data where you store the location where you store the data. Then depending on the distance, you may spend different time to read out the data. So this is very different than the random access memory we talk about here. So this is the random access memory, and the SRAM is one type of the random access memory. DRAM is another type, and we are going to discuss DRAM in the next lecture 18. But again, before we talk about the SRAM cell, let's have some discussions on the features of the SRAM. So SRAM is short for static random access memory, and we talk about what is random access. It's each bit can be accessed independently. And here we are going to talk about the static. What static means? So static means no periodic refresh. So this is respect to the DRAM, where we need the periodic refresh. Or in other words, for the static means after you turn on the power supply, your data pattern will be there, will be static. You can memorize your data. You can store the data like a static pattern. So that means static. One more feature for the SRAM is that it's one type of the volatile memory. So volatile, as we discussed in the last lecture, means if the power supply is removed, you will lose the memory state or your data is gone. So this is a temporal data storage. You cannot store this for a long time. Of course, if you keep your power supply for a long time, then you will have your data there. But normally, if you turn off the power supply, then your data is gone in the SRAM. So any questions so far? So if you have questions, you can use the chat function or you can unmute yourself. All right, so let's move on. So here, this is the SRAM cell circuit we're going to discuss in great details. So here, this is the SRAM cell to store 1 bit data. And it consists of 2 inverters cross-coupled in the middle with 2 access transistors. So here you see those 2 inverters in the middle, and they connected in a loop. So you have, for example, this is N1 node, this is N2 node. And you can store the information, for example, Q at N1, then the N2 node will be Q bar. Because those 2 data will be complementary. So actually you only store 1 bit of the data. For example, if this side is 0, after the top inverter, then the output will be 1. And this 1 will be the input for the bottom inverter, then output will be 0. So this is a stable circuit, and actually it's a latch. We talk about this in the inverter lectures. And if you have the, let's say, even number of the inverters in the loop, it will be stable. If you have odd number inverters in the loop, you know, it's oscillator. The signal is going to oscillate. So here we are going to use these 2 inverters as a latch to latch the data. And then to read the data out, we need to have those access transistor because you need to get the data out through the bitline to the outside of the array. So we need to have this access transistor to function as a bridge between the bitline and the storage node. And this access transistor is controlled by the word line. So here the gate of the access transistor is controlled by the word line. So here is the key feature of the SRAM cell. As you can see here, we only store 1 bit of the data. To make it simpler, we always, let's say, read the data from the bitline using the data stored in the N1 node in the data, because otherwise it's always complementary. You don't carry additional information. So the information is always, let's say, stored in the N1 node. You read out through the bitline. So it's only 1 bit data, either 0 or 1. And to store this 1 bit of data, you see how many transistors do we use here? So you see here 2 inverters. Each inverter is 2 transistors. So here we have 6 transistors in total. Yes, 6. So if you draw out the circuit into the transistor, you will have the red figure to show the transistor level circuit diagram for this SRAM cell. And here we have some terminologies for this circuit, and we are going to discuss in more details. So first of all, we talk about N1 and N2 nodes. So those 2 nodes are the data storage nodes because we store the data there. And as I just said, it's easier to always look at the N1 node, which is attached to the bitline, because the other one is always complementary. And then we have the bitline and bitline bar, because this one is always complementary, so we have a bitline bar. So this is unique in the SRAM. We have 2 bitlines because of the symmetric structure. This everything is, can be mirrored if you draw a line in the middle, then it can be mirrored. So this is symmetric. It's unique in the SRAM design. Later you see the DRAM, we don't have the bitline bar. But for SRAM, we have this one word line, which control both those two access transistors. So here we're going to give a few names to those transistors. And here, those 6 transistors, out of those 6, 4 are NMOS. So those 4 are NMOS. And then the top 2 are PMOS. So why is that? Because here, for example, the inverter 1, those 2 red transistors, NMOS pull down, PMOS pull up. So here we give the name for the NMOS transistor, and NMOS transistor is for pull down NMOS, and we have this PD1 and PD2 NMOS for the pull down. So here those 2 blue transistors are for the inverter 2, and here we have 2 PD, one is PD1, one is PD2, both NMOS, and pull up PMOS. PMOS is to pull up the signal. So then we have PU1 and PU2. So those 4 transistors form this cross-coupled match. And then here you see the connections, a little bit complicated, but it's really a cross-coupled connection, because the output for the inverter 1, which is here, which is N1, this N1 goes to the input of the inverter 2, which is here, control the gate of the PD2 and PU2. So this is really cross-coupled. Similarly, this N2 goes to the input of the inverter 1. So this is cross-coupled. And then we have 2 additional transistors, those 2 access transistors in green. So we call this pass gate because it passes the signal from the storage node N1 to the bitline, which is to the outside of the memory array. So this is the pass gate, and of course we have PG1 and PG2. So I got one question, that is, can we use PMOS for the pass gate? So theoretically, yes, you can use that, but in practice, we don't use that. The reason is that NMOS is faster, so we want to use the NMOS to do that. PMOS is slower, as you know. So in practice, we want to use the faster transistor, so that's why we use NMOS. So I got another question. Do we use the same bitline for read-write operation? The same bitline. Okay, we are going to discuss the details of the read and write operations in the next. Just stay tuned. So here we have the pass gate and a PG, and we call it PG. Next, we're going to discuss those operations. Before we talk about the read and write, actually there's one more operation for the SRAM, which is hold, means you do nothing. Okay, if you do nothing, you just want to hold the data there. So if you just want to hold the data as a memory, then what you need to do here is to cut off those 2 pass gates, because those 2 pass gates is a collection or bridge from the internal storage to the outside. If you don't want to change your data, you want to hold the data, then you don't want any communication to the outside. So what you want to do here is just to turn off the word line. So the word line is 0, ground. So if word line is 0, then those 2 pass gates are turned off. So those 2 pass gates are turned off because those 2 pass gates are NMOS, and you apply 0 voltage to the gate. of the NMOS is off. So if those two transistors are off, it's more like an open circuit. Then what is left is only those two coupled inverter in the middle. And then this is a latch, as we discussed. It's a stable circuit, so you can hold the data. In this particular example, N1 stores 0, N2 stores 1. Okay. So this is a hold operation. And let me stop for now because I want to make multiple clips of the video.